ಶುರು ಮಾಡೋದಾ ಸರ್? ಹಲೋ ಸರ್, ಶುರು ಮಾಡೋದಾ ಸರ್?
Yes, sir. Yes.
PPT ಶೇರ್ ಮಾಡ್ಕೋತೀರಿ ಸರ್? So, good afternoon, sir. Hello, sir. Hello.
Hello, sir. Hello. Matadi, sir.
Sir, good afternoon, sir. Good afternoon, sir.
Good afternoon, sir.
So, good afternoon, everybody. So, ಇವತ್ತಿನ ಉಪನ್ಯಾಸ ಕಾರ್ಯಕ್ರಮದಲ್ಲಿ ಡಾಕ್ಟರ್ ಚಂದ್ರಶೇಖರ್ ಶೆಟ್ಟಿ ಸರ್ ಅವರು ಎಲಾಸ್ಟಿಸಿಟಿ, ಬಿಹೇವಿಯರ್ ಆಫ್ ಎಲಾಸ್ಟಿಸಿಟಿ ಆಫ್ ರಬ್ಬರ್ ಇನ್ ಸಾಲಿಡ್ಸ್ ಈ ಒಂದು ವಿಷಯದ ಮೇಲೆ ಉಪನ್ಯಾಸ ನೀಡಲಿದ್ದು, ಅವರನ್ನ ಅಕಾಡೆಮಿಗೆ ನಮ್ಮ ತುಂಬು ಹೃದಯದ ಸ್ವಾಗತದಿಂದ ಸ್ವಾಗತಿಸುತ್ತಾ, ಸೊ ವೆಲ್ಕಮ್ ಟು ಅಕಾಡೆಮಿ ಸರ್.
ಎಲ್ಲರಿಗೂ ನಮಸ್ಕಾರ. ಮೊದಲನೇದಾಗಿ ಈ ಉಪನ್ಯಾಸ ಮಾಲಿಕೆಯ ಇಲಾಸ್ಟಿಕ್ ಬಿಹೇವಿಯರ್ ಆಫ್ ಸಾಲಿಡ್ಸ್ ಎಂಬ ವಿಷಯದ ಬಗ್ಗೆ ಮಾತಾಡಲಿಕ್ಕೆ ಅವಕಾಶ ಕೊಟ್ಟಂತ KSTಯ ಪದಾಧಿಕಾರಿಗಳಿಗೆ ವಂದನೆಗಳು. ಇವತ್ತು ನಾವು ಇಲಾಸ್ಟಿಕ್ ಬಿಹೇವಿಯರ್ ಆಫ್ ಸಾಲಿಡ್ಸ್ ಅಂದ್ರೆ ವಸ್ತುಗಳ ಸ್ಥಿತಿಸ್ಥಾಪಕ ಗುಣದ ಬಗ್ಗೆ ಸ್ವಲ್ಪ ಮಾಹಿತಿಯನ್ನು ಪಡೆದುಕೊಳ್ಳುವ. ನಮಗೆ ಗೊತ್ತಿರುವ ಹಾಗೆ ವಸ್ತುಗಳನ್ನು ನಾವು ಘನ ವಸ್ತುಗಳು, ದ್ರವ ವಸ್ತುಗಳು ಮತ್ತು ಅನಿಲ ವಸ್ತುಗಳು ಎಂದು 3 ವಿಧವಾಗಿ ವಿಂಗಡಿಸ್ತೇವೆ. ನಮಗೆ ಗೊತ್ತಿದ್ದ ಹಾಗೆ ಅನಿಲಗಳಿಗೆ ಮತ್ತು ದ್ರವ ವಸ್ತುಗಳಿಗೆ ಅವು ಯಾವ ಪಾತ್ರೆಯಲ್ಲಿ ಇದ್ದಾವೆ ಆ ಶೇಪ್ ಅದಕ್ಕೆ ಬರ್ತದೆ, ಆ ಆಕಾರ ಬರುತ್ತವೆ. ಆದರೆ ಘನ ವಸ್ತುಗಳಿಗೆ ಅದರದ್ದೇ ಆದ ಆಕಾರಗಳಿವೆ. ನಾವು ಬಹಳ ಮುಖ್ಯವಾಗಿ ಇವತ್ತಿನ ದಿನ ಈ ಘನವಸ್ತುಗಳ ಆಕಾರ ಮತ್ತೆ ಸ್ಥಿತಿಸ್ಥಾಪಕ ಗುಣದ ಬಗ್ಗೆ ಮಾತಾಡುವಂತ ಉದ್ದೇಶ ಇಟ್ಕೊಂಡಿದ್ದೇವೆ. ಓಕೆ, ನಾವು ಏನೆಲ್ಲ ಮಾತಾಡ್ತೇವೆ ಅಂತ ಜಸ್ಟ್ ಒಂದ್ಸಲ ನೋಡೋಣ. ಇವತ್ತು ಫಸ್ಟ್ ರಿಜಿಡ್ ಬಾಡೀಸ್ ಅಂದ್ರೆ ಘನ ವಸ್ತುಗಳು. ವಾಟ್ ಇಸ್ ಮೀನ್ ಬೈ ಇಲಾಸ್ಟಿಸಿಟಿ, ಸ್ಥಿತಿಸ್ಥಾಪಕ ಗುಣ. ಇಲಾಸ್ಟಿಕ್ ಡಿಫಾರ್ಮೇಶನ್, ವಸ್ತುವಿನ ಆಕಾರದಲ್ಲಿ ಆಗುವಂತಹ ವ್ಯತ್ಯಾಸಗಳು. ಪ್ಲಾಸ್ಟಿಸಿಟಿ ಅಂದ್ರೆ ಏನು ಅಂತ ಹೇಳಿ, ದೆನ್ ಇದಕ್ಕೆ ಮೂಲಭೂತವಾಗಿ ಕಾರಣವಾಗುವಂತಹ ಸ್ಟ್ರೆಸ್, ಸ್ಟ್ರೈನ್, ಮಾಡ್ಯುಲಸ್ ಆಫ್ ಇಲಾಸ್ಟಿಸಿಟಿ, ಪಾಯ್ಸನ್ಸ್ ರೇಷಿಯೋ, ಇಲಾಸ್ಟಿಕ್ ಪೊಟೆನ್ಷಿಯಲ್ ಎನರ್ಜಿ ಇನ್ ಎ ಸ್ಟ್ರೆಚ್ಡ್ ಸ್ಟ್ರಿಂಗ್. ಈ ವಿಚಾರದ ಬಗ್ಗೆ ನಾವು ಸ್ಥೂಲವಾಗಿ ಮಾತಾಡುವಂತ ಪ್ರಯತ್ನವನ್ನು ಮಾಡುವ. ಈಗ ಮೊದಲನೇದಾಗಿ ನಾವು ವಸ್ತುಗಳ ಆಕಾರವನ್ನು ಬದಲಿಸಲು ಅವುಗಳಿಗೆ ಬಲವನ್ನು ಪ್ರಯೋಗ ಮಾಡಬೇಕಾಗುತ್ತದೆ. ಉದಾಹರಣೆಗೆ ನಾವು ಒಂದು ಸ್ಪ್ರಿಂಗ್ ಅನ್ನು ತೆಗೆದುಕೊಂಡು ಅದಕ್ಕೆ ಬಲ ಪ್ರಯೋಗ ಮಾಡಿ ಅದನ್ನು ಇದು ಎಳೆದರೆ ತಕ್ಷಣಕ್ಕೆ ಅದು ಉದ್ದವಾಗಿ ಮಾರ್ಪಾಡಾಗುತ್ತದೆ. ಮತ್ತೆ ಆ ಬಲವನ್ನು ನಾವು ಬಿಟ್ಟಾಗ ಪುನಃ ಅದರ ಒರಿಜಿನಲ್ ಶೇಪಿಗೆ ಹೋಗ್ತದೆ. ಇಟ್ ಕ್ಯಾನ್ ರಿಗೇನ್ ಇಟ್ಸ್ ಒರಿಜಿನಲ್ ಶೇಪ್. ಅಂದ್ರೆ ಆ ವಸ್ತು ನಾವು ಬಲ ಪ್ರಯೋಗ ಮಾಡಿದಾಗ ಉದ್ದದಲ್ಲಿ ವ್ಯತ್ಯಾಸ ಆಗಿ ಹೆಚ್ಚಾಗಿ ನಂತರ ಪುನಃ ಅದ ಸ್ಥಿತಿಗೆ ಬರ್ತದೆ ಯಾವಾಗ ನಾವು ಬಲವನ್ನು ವಾಪಸ್ ತೆಗೆದುಕೊಂಡಾಗ. ಇದು ಬಹಳ ಸಣ್ಣ ಉದಾಹರಣೆ. ಸ್ಥಿತಿಸ್ಥಾಪಕ ಗುಣ ಅಂದ್ರೆ ವಸ್ತುಗಳು ಅದರ ಒರಿಜಿನಲ್ ಸ್ಥಿತಿಗೆ ಅಥವಾ ಮೂಲ ಸ್ಥಿತಿಗೆ ಮರಳುವುದನ್ನು ಸ್ಥಿತಿಸ್ಥಾಪಕ ಗುಣ ಅಂತ ಹೇಳ್ತೇವೆ. ಈಗ ಕೆಲವು ಸರಿ ನಾವು ನೋಡಬಹುದು ಈ ವಸ್ತುಗಳು ಅವುಗಳ ಸ್ಥಿತಿಗೆ ಬರಲು ಸಾಧ್ಯವೇ ಆಗುವುದಿಲ್ಲ. ಅಂದರೆ ಟೋಟಲ್ ಆಗಿ ಮಾರ್ಪಾಡಾಗಿ ಬಿಡ್ತದೆ, ಕಂಪ್ಲೀಟ್ ಡಿಫಾರ್ಮೇಶನ್ ಆಗಿ ಬಿಡ್ತದೆ. ಇಂತಹ ಪರಿಸ್ಥಿತಿಗೆ ಪ್ಲಾಸ್ಟಿಸಿಟಿ ಅಂತ ಕರೀತೇವೆ. ಇಲಾಸ್ಟಿಸಿಟಿ ಮತ್ತೆ ಪ್ಲಾಸ್ಟಿಸಿಟಿ. ಇಲಾಸ್ಟಿಸಿಟಿ ಅಂದ್ರೆ ದ ನೇಚರ್ ಆಫ್ ದ ಬಾಡಿ ಟು ರಿಗೇನ್ ಇಟ್ಸ್ ಒರಿಜಿನಲ್ ಶೇಪ್ ವೆನ್ applied force is removed. Suppose the body maintains the permanent shape after the removal of the applied force also, then we call that body as a plastic body. ಇದು ಬೇಸಿಕ್ ಡೆಫಿನಿಷನ್ ಆಫ್ ಪ್ಲಾಸ್ಟಿಸಿಟಿ ಅಥವಾ ಇಲಾಸ್ಟಿಸಿಟಿ. ಈಗ ಇಲಾಸ್ಟಿಕ್ ಡಿಫಾರ್ಮೇಶನ್ ಆಗಲಿಕ್ಕೆ ಏನು ಕಾರಣ? ವಾಟ್ ಇಸ್ ದ ರೀಸನ್ ಫಾರ್ ಡಿಫಾರ್ಮೇಶನ್ ಆಫ್ ದ ಬಾಡಿ? ಯು ನೋ ದಟ್ ಈ ವಸ್ತುಗಳು ಅಣುಗಳಿಂದ ಮಾಡಲ್ಪಟ್ಟಿವೆ. ಅಣುಗಳ ಮಧ್ಯೆ ಒಂದು ಬಲ ಇದೆ, ಬಾಂಡ್ಸ್ ಇದೆ. ಆ ಬಾಂಡ್ಸ್ಗಳು ನಾವು ಬಲ ಅಪ್ಲೈ ಮಾಡಿದಾಗ, ಬಲವನ್ನು ಪ್ರಯೋಗ ಮಾಡಿದಾಗ ಅವು ಸಂಕುಚಿತಗೊಳ್ಳುತ್ತವೆ ಅಥವಾ ವಿಕಸನಗೊಳ್ಳುತ್ತವೆ. ಅದು ಯಾವ ಮೂಲ ಜಾಗದಲ್ಲಿ ಇರಬೇಕಿತ್ತು ಆ ಜಾಗದಲ್ಲಿ ಇಲ್ಲದೆ ಹೋದಾಗ ಅವುಗಳಲ್ಲಿ ನಾವು ವಿಕಸನವನ್ನು ಕಾಣ್ತೇವೆ. ಏನಾಗ್ತದೆ ಈ ಅಣುಗಳಿಗೆ? when you apply force, ಬಲವನ್ನು ಪ್ರಯೋಗ ಮಾಡಿದಾಗ ಈ ಅಣುಗಳ ಮಧ್ಯೆ ಘರ್ಷಣೆ ಸಂಭವಿಸಿ ಅವುಗಳು ಒತ್ತಡಕ್ಕೆ ಒಳಗಾಗ್ತವೆ. ಸ್ಟ್ರೆಸ್ is developed in the crystal structure of the material. ಸ್ಟ್ರಕ್ಚರಿಗೆ, ಅದರ ಒರಿಜಿನಲ್ ಕ್ರಿಸ್ಟಲ್ ಸ್ಟ್ರಕ್ಚರ್ ಮೇಲೆ ಬಲ ಪ್ರಯೋಗ ಮಾಡಿದಾಗ ಸ್ಟ್ರೆಸ್ ಡೆವಲಪ್ ಆಗ್ತದೆ. ಸ್ಟ್ರೆಸ್ ಅಂದ್ರೆ ಏನು? ನಾವು ಒಂದು ನಿರ್ದಿಷ್ಟ ಪ್ರಮಾಣದ ಬಲವನ್ನು ಒಂದು ನಿರ್ದಿಷ್ಟ ಜಾಗಕ್ಕೆ ಅಥವಾ ವಿಸ್ತೀರ್ಣಕ್ಕೆ ಅಪ್ಲೈ ಮಾಡಿದಾಗ ನಾವು ಏನು ಹೇಳ್ತೇವೆ ಅಂದ್ರೆ ಅದು ಸ್ಟ್ರೆಸ್ ಅಂತ. ಮ್ಯಾಥಮೆಟಿಕಲಿ ವಿ ರೈಟ್ ಇಟ್ ಆಸ್ ಸ್ಟ್ರೆಸ್ ಈಸ್ force by area. Force by area, that is stress. Suppose you call force by F, area by A. Force by area is stress. This is the magnitude of the stress. Larger the force, larger will be the stress developed. Similarly, large force is applied for a smaller area, then also you find that very large stress is applied. ಇದು ಸ್ಟ್ರೆಸ್ಸಿನ ಡೆಫಿನಿಷನ್. ನಾವು ಈ ಸ್ಟ್ರೆಸ್ ಡೆಫಿನಿಷನ್ ಹೇಳುವಾಗ ಈ ರೀತಿ ಹೇಳ್ತೇವೆ ನೋಡಿ. when a body is subjected to a deforming force, a restoring force is developed within the body. This restoring force is equal and opposite to the direction of the applied force. The restoring force is known as stress. It has to regain its shape. ಅದಕ್ಕೆ ರಿಸ್ಟೋರಿಂಗ್, ವಾಪಸ್ ಬರುವಂತಹ ಗುಣ, ಸ್ಥಿತಿಸ್ಥಾಪಕ ಗುಣ. If F is the applied force normal to a cross section area A, then magnitude of the stress is equal to F divided by M. ಇದನ್ನು ನಾವು ಪಾಸ್ಕಲ್ ಯೂನಿಟ್ ಅಲ್ಲಿ ಮೆಷರ್ ಮಾಡ್ತೇವೆ. ಪಾಸ್ಕಲ್ ಅಂದ್ರೆ ನ್ಯೂಟನ್ per meter square. Newton is force, meter square is area. Dimensional formula ಇದರದು m l to the power -1 e to the power -2. That is the dimension formula of stress. ಈಗ ಇನ್ನೊಂದು ಬಹುಮುಖ್ಯವಾಗಿ ನಾವು ತಿಳ್ಕೊಳ್ಬೇಕಾದ ವಿಧಾನ ಅಂದ್ರೆ ವಿಷಯ ಅಂದ್ರೆ the longitudinal stress. What do you mean by longitudinal stress? Longitudinal stress. Longitudinal stress ಅಂದ್ರೆ ಒಂದು ವೈರಿಗೆ ನಾವು ಅದನ್ನು ಉದ್ದ ಮಾಡಲಿಕ್ಕೆ ಅಪ್ಲೈ ಮಾಡುವಂತ ಫೋರ್ಸ್, ದಟ್ ವಿಲ್ ಬಿ ಕಾಲ್ಡ್ ಆಸ್ ಲಾಂಗಿಟ್ಯೂಡಿನಲ್ ಸ್ಟ್ರೆಸ್. ಅದೇ ರೀತಿ ಸ್ಟ್ರೆಸ್ ಅನ್ನು ನಾವು ಫೋರ್ಸ್ ಬೈ ಅಪ್ಲೈಡ್ ಏರಿಯಾ ಅಂತ ಮೆಷರ್ ಮಾಡಿದ್ರೆ ಇನ್ನೊಂದು ಕ್ವಾಂಟಿಟಿ ಇದೆ, ದಟ್ ಇಸ್ ಕಾಲ್ಡ್ ಸ್ಟ್ರೈನ್. Strain. Therefore, I say what is longitudinal strain. In general, strain ಅಂದ್ರೆ ಒರಿಜಿನಲ್ ಆಗಿ ಇದ್ದಂತಹ ಅಳತೆ ಮತ್ತೆ ಮಾರ್ಪಾಡದ ಅಳತೆ ಇವುಗಳ ರೇಷಿಯೋ ತೆಗಿಬೇಕು. ಈಗ ಲಾಂಗಿಟ್ಯೂಡಿನಲ್ ಸ್ಟ್ರೈನ್ ಅಂದ್ರೆ ಸಪೋಸ್ you have a wire of length L, you have a wire of length L, you apply a force in this direction, pull by applying a force, it is increased by a small extent. Now this is increased to a larger force. Suppose this is L, change in length is called delta L, then say delta L by L is called longitudinal strain. That is changing the length to the original length. ಯಾಕೆ ಲಾಂಗಿಟ್ಯೂಡಿನಲ್ ಸ್ಟ್ರೈನ್ ಅಂತ ನಾವು ಕರೀತೇವೆ? ನಮ್ಮ the applied force is applied to make the wire lengthier along the length we applied. Therefore, the name longitudinal strain. ಅದೇ ರೀತಿ we can have other strains. What are the other strains? Tangential strain. For that, we'll discuss with this few pictures. Look at this. The first one, I am showing you a cylinder like a wire of length L. A force is applied in either direction, from the top as well as from the bottom. Then you see the length is increased by delta L. Delta L is the length, increased length. Therefore, as I told you, delta L by L will give you longitudinal strain. Other ರೀತಿ shearing strain. Look at this second diagram. I have a cylinder of length L. Now I apply a force in such a manner that this end of the cylinder is pulled towards right, the bottom part is pulled towards left. What very important to remember here, the base of the cylinder is kept constant. Base ಅಲ್ಲೇ ಇದೆ, ಅದು ಮೂವ್ ಆಗೋದಿಲ್ಲ. ನಾವು ಬೇಸ್ನಿಂದ ಲೆಫ್ಟಿಗೆ ಅಪ್ಲೈ ಮಾಡಿದ್ರೆ ಫೋರ್ಸು, ಅದರ ತುದಿ ಭಾಗದಿಂದ ನಾನು ರೈಟಿಗೆ ಫೋರ್ಸ್ ಅಪ್ಲೈ ಮಾಡಿದ್ರೆ ಏನಾಗ್ತದೆ, ಈ ಸ್ಟ್ರೈಟ್ ಇದ್ದ ಸಿಲಿಂಡರ್ ಯು ಕ್ಯಾನ್ ಸಿ ಇಟ್ ಇಸ್ ಬೆಂಡ್ ಟವರ್ಡ್ಸ್ ರೈಟ್, ಮೇಕಿಂಗ್ ಎನ್ ಆಂಗಲ್ ಥೀಟಾ ಅಟ್ ದಿಸ್ ಆಕ್ಸಿಸ್. It is a delta x, the displaced position of the cylinder. It is 0 here, it is delta x. Therefore, if I take delta x by L, then it can measure in terms of tan theta, that is nothing but shearing strain. Shearing strain. This is an important point to remember. Shearing strain will take the object to one side, it is a base is fixed constant. That is the definition of shearing strain. Similarly, for most of the objects, if you apply large force also, theta will be very small. Then you can say tan theta is small. This quantity is delta x by L. You can equate. You know that theta is small means tan theta can be replaced with theta itself. Therefore, delta x by L can be directly used to measure the shearing strain. Similarly, we look at the third example here. This is, say, normally we have a thick size textbooks. Suppose you press the top of the front page of the or the top side of the book, then you see it will slightly move downwards, right? That means you can see the third picture here. This picture you can see here. This type of stress is referred as hydraulic stress, hydraulic stress. Or you can say change in volume divided by delta original volume. Okay, change in volume divided by original value. Of course, here also you second example, you can see the example which I told you, the example of book, where you find that there are examples of this type also, correct? The third example you can see here. This is an example of a shearing only, not a hydraulic. This is example of a shearing stress. Okay, shearing stress. The last example, hydraulic stress I'm talking about here, the last one, where you see that object is getting the force in all the directions, still there is no change in the shape of the body, but the surface of the body experiences a force. As a result, there will be change in volume, we can say delta V. Here, what is that? There, delta V, there is a change in volume divided by the original volume. That is called hydraulic stress, strain. As a result, hydraulic stress which results to hydraulic strain also. Okay, therefore delta V by V is we also call it as volume strain. Okay, therefore stress is force by unit area. Strain is depending on how the strain is developed. Shearing strain, longitudinal strain, or volume strain can be discussed. Okay, now very important thing is what is the extent of force you can apply on a body. That is understood by very famous law that is called Hooke's law. You can see here Hooke's law. What is Hooke's law? Say Hooke is a person who studied the strain and stress relationship. He found that for most of the materials, stress is proportional to strain. Okay, stress is proportional to strain. But whether it is true everywhere, it is not true everywhere. There is a limit. Therefore, what we say is within elastic limit. Within elastic limit, we say stress is proportional to strain. Therefore, if I say stress, that is equal to some constant into strain. Okay, some constant into strain. This is called Hooke's law. But what is meant by elastic limit? That is very, very important for any material to say whether it's a good material or not. The entire property of Hooke's law can be explained with the help of this graph. Just refer to this graph. I have y-axis stress. In the x-axis we have strain. Okay. You see, for a very small applied force, stress is to be smaller. As a result, stress is linear to strain. You can see from 0 to A, stress is proportional to strain. It's a linear relationship. That means within this elastic limit, if you apply the force, the body can come back to the original shape. It can regain its original shape. That is called elastic limit. Very, very important point. Now, here the body can return to the original shape once you remove the applied force. That is a linear region, that is between 0 to A. Look at A to B here, between A to B. A to B also, somewhat it follows the Hooke's law, A to B. But B is called yield point. That means it is the elastic limit. Yield point, B is called yield point. It is written here, yield point, which is the elastic limit. And corresponding stress can be called as yield stress or yield strength of the material. If you remember, suppose if you apply a force which is more than the point A, beyond A, you apply, till B, body can again regain its shape. That is the important point to be remembered. You can get back the original shape till you apply the strain that is equal to B. Why it's called yielding point? After that point, if you extend the strain, if you increase the strain, then body cannot return to the original shape. That is called permanently, it will be deformed. Permanent deformation takes place. You say permanent deformation takes place. And if you go beyond, you see the fracture point, body will break into two because of the excess of strain applied. Therefore, we understand the point that say elastic nature is maintained between 0 to B, at least 0 to A and A to B also. Later, it will go to plastic point. Okay, plastic point. Then, if you think of the point D and E, say that is called brittle. Brittle material becomes brittle means any time it will break into pieces. Okay, therefore you remember a material can become elastic, it will lose elastic property if it is brittle, because after brittle state, body will completely broken into pieces, into two, because of the applied stress. Now, very important thing, say by knowing what is the elastic limit, how much it can withstand the force applied. Hook law plays an important role in selecting a material for any purpose, like a construction of a bridge, construction of a beam, construction of a house, or any strong material you require for a particular application. Then the material to be selected based on the properties of elastic constants. Okay, here stress is equal to K into strain, and this K, no, this K is called modulus of elasticity. Modulus of elasticity. Modulus of elasticity. Because that will determine whether material is elastic or not. And based on how you apply the force, you can decide what is the nature of elastic modulus. We have to study three different types of elastic modulus: Young's modulus, bulk modulus, and shear modulus. This is also important one. Now, next, what I am trying to say is, say for a material, solid material like iron, copper, silver, you have a precise values of elastic constant. Whether this is true for living tissues also. Say we have various body tissues in our body. Particularly, if you look at observe the heart, there the muscles are so powerful to pump excess of blood. Sometimes they will pump excessively beyond the limit of elastic changes. Such observation also people studied. Say here, if you look at this one particular diagram, stress strain curve for an elastic tissue of aorta. Aorta is a big pipe which supplies blood in our heart. Therefore, here stress strain relationship is not at all matching. It is having very better properties because Hooke's law is not valid there, or it doesn't follow the Hooke's law. And it can work well beyond the plastic region also. You can see it can work well beyond the plastic region. That is the properties of tissues of human body, okay? Tissues or muscles. If you look at the muscles of human body or tissues, this type of elastic behavior is observed. And similarly, say we make use of rubber, example of rubber, which is having looks highly elastic. Of course, we don't classify under elastic property. They are classified as a special class of materials called elastomers. Elastomers. What are elastomers? They are the materials which can withstand large strain. Which can withstand large strain. They can work beyond the plastic limit. Therefore, nowadays people are preparing artificial elastomers, artificial materials which are acting like elastomers. They can substitute human tissue, human body organs can be substituted by this material. That class of materials are referred as elastomers. They are more elastic in nature in general. In common sense, it is more elastic in nature. I hope you are getting what I am trying to say about Hooke's law. Next, depending on how you apply the force, we have three different types of modulus. First one, Young's modulus. So what do you mean by Young's modulus? The Young's modulus is denoted by a letter Y, Young's modulus. Suppose you apply force to increase the length, that's called tensile force, which is increasing the length. Imagine a wire you have, imagine a cylinder you have. You apply the force so that it increases in length. That is called tensile stress, which will lead to a longitudinal strain. Tensile stress, which lead to longitudinal strain. Therefore, if you take the ratio of tensile stress, say Y is equal to tensile stress divided by longitudinal strain. Okay, longitudinal strain. Tensile stress by longitudinal strain. That is called Young's modulus. Ratio of tensile stress to longitudinal strain is called Young's modulus. Suppose I denote this by sigma and this divided by epsilon, then Y is equal to sigma divided by epsilon. The ratio of tensile stress to longitudinal strain is referred as Young's modulus. Therefore, if you calculate that in terms of force by applied area, say this is equal to force divided by area, force by area. Here, change in length divided by the original length. Therefore, this will be F into L divided by A into delta L. F into L into A into delta L. L is the original length, delta is the change in length, and F is the applied force, A is the area of cross section. And it is measured in terms of Newton per meter square, because one L cancels there, force by area, Newton per meter square is the unit to calculate Young's modulus. What is very important here is, you look at this chart there, I given a table here. Here, there are various substances are given in the first column: aluminum, copper, iron, steel, glass, concrete, wood, bone, polystyrene, like this. Second column, density is given. You know, the material has got a particular density. How the package is done depending on the density is there. Third column talks about Young's modulus. Look at the numbers. Aluminum is 70 into 10 to the power 9. Very important point, remember, it's a very large value. Young's modulus is very large. You should not forget this 10 to the power 9. Remember, when we write in a table, we write them together. Here, okay, you can see the first column. I hope you are able to see the first column here. First column, say here, it is always up 10 to the power 9 is there. Remember, 10 to the power 9, very important, Newton per meter square everywhere. 17 to the power 9. Copper 110 into the power 9. Iron 190 into the power 10. Steel is say 200 into 10 to the power 9. Okay, 200 into 10 to the power 9. Therefore, remember, steel has got highest Young's modulus. Therefore, steel is used for most of the construction material. Is used as a construction material, whether it's a beam, whether it's a bridge, whether it's a house, or if you want to make an almirah, everything steel is used because it has got highest Young's modulus. It can withstand force to a very large extent. Similarly, the ultimate tensile strength is also very large here, 400. in 10 to the power 6 Newton per meter square for this material. Whereas look at the other materials like glass, concrete, wood, bone, this is very, very small. Polystyrene is very much brittle because 10 to the power 9 only, it's the value of Young's modulus. Therefore, by knowing Young's modulus, we get an idea about what type of material it is, how strong it is, how much force it can withstand for a given application. That is very important. You can refer to the textbooks where you see lot of problems where you determine Young's modulus of materials. Very straightforward, problems are very straightforward. You have a wire of area of cross section A. Wire means you have pi r square is the area of cross section. Then elongation takes place. As a result, you see that what is the applied force, what is the change in area. Then you can calculate how much change in length took place. Accordingly, you can calculate what is the Young's modulus of that material. Okay. Next one, shear modulus. What do you mean by shear modulus? When I say shear modulus, it talks about how the shearing stress and shearing strain are related. As I told you, so if you have a material like this, here if you have a material, think of a box you have a box, okay? You have a box. Suppose you apply force over here, keeping this base part constant. Then I told you it will get shifted like this. No, it will get shifted to a small extent. You can see, and this makes an angle theta, right? The previous example I explained you. Therefore, see, shear modulus is calculated using a notation G, that is shearing stress strain. Okay, shearing stress divided by shearing strain. That means what extent deformation takes place. Therefore, if you take the same formula, F by A is the shearing stress. Here, as I told you, delta X by L, right? No, delta X by L. Because I told you theta is very small, therefore that is delta X by L only you can take. Hence, you will find that F into L, okay, divided by A into delta X. That will give you the expression for shear modulus, Again, its unit is Newton per meter square. Newton per meter square or Pascal is the unit of shear modulus. That is the second elastic constant. Again, you look at the numbers here: aluminium, brass, copper, glass, iron, lead, nickel, steel, tungsten, wood, everything is given. You look at the shear modulus of certain material. Again, you would remember it is 10 to the power 9 is associated with each number. 25 into the power 9, 36 into the power 9. Look at iron, it is having 70 into the power 9 Newton per meter square. Whereas tungsten is highest it has, it is 150 into 10 to the power 9 Newton per meter square. That is the best material for particular application where shear modulus is involved. That is the second type of example, second type of elastic modulus. Then we go for the third type, okay? Third type of elastic modulus, that is called bulk modulus. What is bulk modulus? Bulk modulus referred with the symbol B. Here, very important thing is, you see that hydraulic stress you applied, which led to a volume change. Hydraulic stress is applied, which led to the volume change. Therefore, if you look at the ratio of hydraulic stress to hydraulic strain, okay, hydraulic stress to hydraulic strain, okay, bulk modulus we are talking about. V hydraulic stress B is, as I told you, hydraulic stress to hydraulic strain, hydraulic stress to hydraulic strain. If you take the ratio of this, you will get a constant called bulk modulus. Therefore, here B is represent a normal. Hydraulic stress is in terms of pressure, you can measure P divided by delta V divided by V. The strain is delta V by delta V by delta V by V. That is the hydraulic strain. Again, this also measured in terms of Newton per meter square, and it is very important because the ratio of this, if you take reciprocal of this, reciprocal of bulk modulus. Okay, so when you take a reciprocal of bulk modulus, that is called as compressibility. Compressibility. So what is the amount of compression you can give to that material? That is decided by the bulk modulus. It is reciprocally you have to take 1 by B. 1 by B if you take, that will be compressibility. K we write. K is 1 by B. It is very important. What extent you can compress the body by applying pressure in all the directions, which will lead to change in the volume. That is called bulk modulus. You can see, look at the table again, bulk modulus of few materials. Again, here you see the nickel and steel. Nickel has 260 into 10 to the power 9 meter per square, Newton per meter square. Steel has 160 into 10 to the power 9 Newton per meter square. Whereas you look at the liquid has got smaller value, bulk modulus, that is 2.2, ethanol 0.9, carbon disulfide 1.56 into the power 9, like that. Whereas glass has got least bulk modulus, that is air. Therefore, we say air cannot be compressed. Air can be compressed to maximum extent. Bulk modulus of air is very small. As a result, it has got larger compressibility, because say 1 into 10 to the power minus 4 is the bulk modulus. If you take the reciprocal of that, it becomes 10 to the power 4, 10,000. Therefore, compressibility of air or any gas is much more compared to liquids. Therefore, you would remember one important point is compressibility of solid is the least, compressibility of liquid is next comes, whereas air can be compressed to maximum limit, maximum extent you can compress the air. These are the three different types of elastic moduli of the materials. After knowing this elastic modulus of material, some more important things we'll try to understand. I hope you are getting what I am trying to say. One important thing is Poisson's ratio. What is Poisson's ratio? This constant also takes care of some of the important application of the solids in our day-to-day life. Okay. If you see the strain, when you apply perpendicular to applied force, called lateral strain. If you apply it in a perpendicular direction, we call it a lateral strain. Therefore, Poisson pointed out that within the elastic limit, lateral strain is directly proportional to longitudinal strain. What is observed is lateral strain and longitudinal strain. Okay. They are having constant ratio. Ratio of lateral strain to longitudinal strain is a constant, that is called Poisson's ratio. We call it as Poisson's ratio. Therefore, how you can measure the Poisson's ratio? That can be measured in terms of length. Again, say delta D, if I did delta D divided by D is the lateral strain divided by delta L by L, that is the longitudinal strain, correct? Lateral strain divided by longitudinal strain. Then this will be delta D into L divided by delta L into D. Again, this has got no dimension. The dimensionless unit, okay? No dimension, because numerator and denominator, the dimension cancels. Poisson's ratio has no dimension. And for steel, it has a particular value for steel. That value is also important. The maximum value, that is for steel, it is 0.282. You can see 0.30. Poisson's ratio of steel. Okay. Poisson ratio of steel is 0.28 to 0.30. That is the important value. Whereas if you think of an aluminium alloy, it will be about 0.33. It has not having any unit. I hope what I am trying to say you are able to follow. The three elastic moduli and finally the Poisson's ratio. It is another important observation by Poisson. He observed lateral strain to longitudinal strain is constant for most of the material. That is an important observation. Okay. Next what? Next very important thing I want to discuss here. Now, because of this applied force, what type of energy can be stored in a stretched string? You have, think of a string, okay, which is stretched between the two ends. Okay, you have two strings, this wire of say aluminium or iron or a steel. It is stretched between the two points. Therefore, you see it is under tensile stress now. Okay, it is under tensile stress because you have pressed it. Therefore, to retain this tensile stress, you have done some work on the material. You are doing some work on the work is done on this material, this wire. That means work is applied on. As a result, you see that it some interatomic forces. Interatomic forces experience this applied stress. As a result, what we say is they try to store an elastic energy. They try to store an elastic energy. How it stores elastic energy? That can be calculated by a small mathematical observation. Suppose initially it has the length L, initial length is L, okay, initial length L, then I say it is changed by a length L. L is the increased length, okay, increased length. After application of the force, it increased by a small letter L. So much length is increased. Therefore, you see, originally L has value 0, 0 to L, increase from 0 to L. Right. So, what is work done? If I calculate work done, W, that is, I integrate between 0 to L. Originally, it was 0 length, no increase in the length. Later, it increased to L. Then, say, it is Young's modulus. Y plays an important role there. Ya into L by L into change in the length dl. That is force. You forces can be calculated by force. Work done is what? Force and displacement. Force is what here? Force is nothing but Young's modulus. From the Young's modulus, you get the force. Right? Young's modulus, Y you have here, that is the F into L divided by A into small l. Correct. Therefore, I replace the force. What is force therefore? Force is nothing but, if I rearrange, then y into A into small l divided by capital L. That's what done. Right now, this is nothing but the force. Force into displacement. dl. Now just I rearrange this. Because 0 to L, after integration you will get L here. Then it becomes nothing but, say, y a divided by L. You have one L here, one more L square it becomes. Now if I look at this and rearrange this, okay, what we can do is, here, look at it. Say, I write it as y a divided by 2 and L square divided by L. Okay. Therefore, always we talk about energy stored in terms of the work done, right? Work done. Therefore, if you look at it, you have half here and you have Young's modulus. Okay, you have Young's modulus and you have strain square and volume of the wire. That is L into A becomes the volume of the wire. Volume of the wire. Correct. Therefore, you see, from finally you get half into stress into strain into volume of the wire. Half into stress into strain into volume of the wire. Therefore, this is the amount of work stored in the stretched wire when you apply the force. I hope you are following what I am trying to say. Okay. Next, one more thing, we'll go for one more aspect, that is how do you measure? Okay. How to measure the Young's modulus of a wire in the laboratory condition? How do you measure Young's modulus of one wire? Here we call the determination of Young's modulus of a wire. Okay, Young's modulus of a wire. How to do it? It's a very simple experiment. See, I have two wires. See, I have a setup where I can hang these two wires. One wire, we call this wire A, okay, wire A, other one wire B. This is wire A and wire B. Correct? Which is fixed here. This I call the reference wire. This is called experimental wire. Okay, reference and experimental wire. Here what I do is, both are connected with some pan so that you can keep the weight here. Okay, both are the same weight. Both are connected with some pan. Pan means ತ್ರಾಸು, ಯಾಕೆಂದ್ರೆ ತೂಕ ಇಡುವಂತ ತ್ರಾಸು. ಈ ತ್ರಾಸಿಗೆ ಏನಿರ್ತೇವೆ ನಾವು, ಫಸ್ಟಿಗೆ ಸ್ವಲ್ಪ ವೇಟ್ ಹಾಕ್ತೇವೆ, ಸ್ವಲ್ಪ ವೇಟ್ ಹಾಕುದು, ಈಕ್ವಲ್ ವೇಟ್ ಎರಡಕ್ಕೂ. ಯಾಕೆಂದ್ರೆ ಈ ವೈರ್ ನೇರವಾಗಿ ಸ್ಟ್ರೆಚ್ ಆಗಿ ನಿಲ್ಲುವಾಗೆ, ವೈರ್ ಅಷ್ಟು ಬಿ ಸ್ಟ್ರೆಚ್ಡ್ ಟೈಟ್ ಡೌನ್ವರ್ಡ್. ಅದಕ್ಕೋಸ್ಕರ ಸ್ವಲ್ಪ ಇದಕ್ಕೆ ವೇಟ್ ಅನ್ನು ತೂಕ ಮಾಡಿ ಇಡುವಂಥದ್ದು. ಇಲ್ಲಿ ಒಂದು ಮೀಟರ್ ಸ್ಕೇಲ್ ಅನ್ನು ಫಿಕ್ಸ್ ಮಾಡ್ತೇವೆ ನಾವು, ಒಂದು ಮೀಟರ್ ಸ್ಕೇಲ್. ಓಕೆ, ಈ ವೈರ್ನ ಹತ್ತಿರ ಅದು ತಾಗಿಕೊಂಡಲ್ಲ, ನೆನಪಿಟ್ಕೊಳ್ಬೇಕು, ಒಂದು ಮೀಟರ್ ಸ್ಕೇಲ್ ಅನ್ನು ಫಿಕ್ಸ್ ಮಾಡ್ತೇವೆ. ಒಂದು ಮೀಟರ್ ಸ್ಕೇಲ್ ಇಲ್ಲಿಂದ ಒಂದು ಪಾಯಿಂಟರ್ ಅನ್ನು ಈಗ ಉಳಿದುಂಟು. ಪಾಯಿಂಟರ್ ನೋಡಿ, ಪಾಯಿಂಟರ್ Okay, on the pointer. At any point of time, this meter scale is there. This pointer will point to a particular number there. Correct? ಅದು ಸ್ಕ್ರೂ ಗೇಜ್ ಇರ್ಬೋದು ಅಥವಾ ಯಾವುದು ಬೇರೆ ಕೂಡ ಇರ್ಬೋದು. ಸಣ್ಣ ಮೀಟರ್ ಸ್ಕೇಲ್ ಅಂದ್ರೆ ಸಣ್ಣ ಸಣ್ಣ ಡಿವಿಷನ್ ಇರುವಂತಹ ಒಂದು ಮೀಟರ್ ಸ್ಕೇಲ್. ನಾವೇನು ನೆಕ್ಸ್ಟ್ ಏನ್ ಮಾಡ್ತೇವೆ ಅಂದ್ರೆ, ಸಿ you have this arrangement in the laboratory. Next what you do is, as I told you in the initially, you place some weight there, both of them some weight, so that wire ನೇರವಾಗಿ ನಿಲ್ಲುವಾಗಿ ಸ್ವಲ್ಪ weight ಹಾಕುವಂಥದ್ದು. ನಂತರ ಏನು ಮಾಡ್ತೇವೆ, we will put some more weight, some known weight here, some more weight will put. Okay, some more weight. Why more weight? So that this will be pulled downwards. ಈಗ ಈ ಪ್ಯಾನ್ ಕೆಳಗಡೆ ಬರ್ತದೆ, ಹಾಗೇನಾಗ್ತದೆ, ಈ ಪ್ಯಾನ್ ಒಟ್ಟಿಗೆ ಫಿಕ್ಸ್ ಆಗಿರುವಂತ ಈ ಮೀಟರ್ ಸ್ಕೇಲ್ ಕೆಳಗಡೆ ಬರ್ತದೆ. ಇಟ್ ವಿಲ್ ಶೋ ಎ ಡಿಫರೆಂಟ್ ಪಾಯಿಂಟ್. ನಾವು ದಿಸ್ ಮೀಟರ್ ಸ್ಕೇಲ್, this pointer will be showing to a new point. From that, what you measure, you can measure what is the elongation takes place. Elongation, that is delta L, increase of the length. Suppose original length L, this is the original length. Okay, original length of the wire is L, elongation is delta L. You can measure by the displacement of this pointer, because ಈ ಮೀಟರ್ ಸ್ಕೇಲ್ಗೆ ನಮ್ಗೆ ಎಷ್ಟು ಕೆಳಗಡೆ ಬಂದಿದೆ ಅಂತ ಗೊತ್ತಾಗ್ತದೆ. ಇದು ಇಂಪಾರ್ಟೆಂಟ್ ಪಾಯಿಂಟ್. ಅದೇ ರೀತಿ ನಮ್ಗೆ ಗೊತ್ತಿದೆ ವಾಟ್ ಇಸ್ ದ ಮಾಸ್ ಅಪ್ಲೈಡ್. ಕರೆಕ್ಟಾ? ವೇಟ್ ಅನ್ನು ನಾವು mg ಅಂತ ತಗೊಳ್ಬಹುದು. ಮಾಸ್ ಇಂಟು ಆಕ್ಸಲರೇಷನ್. ವೇಟ್ ಇಸ್ ಈಕ್ವಲ್ ಟು ಮಾಸ್ ಇಂಟು ಆಕ್ಸಲರೇಷನ್. ಈಗ ನಮ್ಗೆ ನೋಡಿ ಎಲ್ಲ ವಿಚಾರ ಗೊತ್ತಿದೆ. ಈಗ ಆರ್ ಇಸ್ ದ ರೇಡಿಯಸ್ ಆಫ್ ದ ವೈರ್. ಓಕೆ, ರೇಡಿಯಸ್ ಆಫ್ ದ ವೈರ್. ಒಂದು ಸ್ಕ್ರೂ ಗೇಜ್ ತಗೊಂಡು ಈ ವೈರ್ ಇದ್ದು ರೇಡಿಯಸ್, ಎರಡು ಒಂದೇ ಲೆಕ್ಕದ ವೈರ್ಗಳು, ಆದರೆ ನಮಗೆ ಎಕ್ಸ್ಪೆರಿಮೆಂಟಲ್ ವೈರ್ ಇದ್ದು ರೇಡಿಯಸ್ ಅನ್ನು ಮೆಜರ್ ಮಾಡಬೇಕು. ಆರ್ ಇಸ್ ದ ರೇಡಿಯಸ್ ಆಫ್ ದ ವೈರ್. Then what is the area of cross section? Area of cross section, capital A, that is pi r square. Pi r square. So what is Young's modulus? We know that Young's modulus is y is equal to sigma by epsilon. Sigma by epsilon. This is force mg. Right? mg force ಅಂದ್ರೆ ವೇಟ್ ಹಾಕಿದಂಥದ್ದು ಕ್ಯಾಲ್ಕುಲೇಟ್ ಮಾಡಬಹುದು. ಜಿ ಇಂದ ಮಲ್ಟಿಪ್ಲೈ ಮಾಡಿದ ಕೂಡಲೇ ಮಾಸ್. ದೆನ್ ಏರಿಯಾ ಆಫ್ ಕ್ರಾಸ್ ಸೆಕ್ಷನ್ pi r square. You know what is the original length and you know what is the increased length. Correct? Say mg divided by pi r square into L divided by delta L. Say all the parameters is known. m ಅಂದ್ರೆ ಮಾಡಿ ಹಾಕಿದಂತ ಮಾಸ್, acceleration due to gravity, original length, change in length, divided by pi r square here. R is the radius. So from this you can very easily calculate what is the Young's modulus of an experimental wire. You don't require any big experimental setup. You require two wires, two pans, so that you can hang some weight on that, and one screw gauge is required to measure the radius of the wire, and a meter scale with a pointer which will tell you what is the amount of elongation taking place by applying more force. This is one of the simplest experiment which you can do in your laboratory. Probably most of the lab people will do this experiment because it will give you a lot of information, and from this you can learn how very small amount of elongation takes place in the wire. You cannot expect large elongation. ಎಷ್ಟು 1 centimeter ಉದ್ದ ಹೆಚ್ಚಾಗ್ತದ, 1 millimeter ಹೆಚ್ಚಾಗ್ತದ ನೋಡ್ಬೇಕು. Even a millimeter to elongate in the case of a steel wire, you require huge amount of load ಜಾಸ್ತಿ ಬೇಕು. ಲೋಡ್ ಅಂದ್ರೆ ಮಾಸ್ ಜಾಸ್ತಿ ಬೇಕು. ಇದರಿಂದ even you can try with the various different materials. ಒಂದು ಅಲ್ಯೂಮಿನಿಯಂ ವೈರ್ ಮಾಡಿ ನೋಡ್ಬೋದು, ಒಂದು ಕಾಪರ್ ವೈರ್ ಮಾಡಿ ನೋಡ್ಬೋದು, ಒಂದು ಸ್ಟೀಲ್ ವೈರ್ ಮಾಡಿ ನೋಡ್ಬೋದು. ಈಗ ನಿಮ್ಗೆ ಗೊತ್ತಾಗ್ತದೆ ಯಾವುದು ಹೆಚ್ಚು ಇಲಾಂಗೇಶನ್ ಆಗ್ತದೆ, ಯಾವುದು ಕಮ್ಮಿ ಇಲಾಂಗೇಶನ್ ಆಗ್ತದೆ. ಅದು very hard material ಅಂತ ಹೇಳ್ಬೋದು, and you can say it is having the what highest ಯಂಗ್ಸ್ ಮಾಡ್ಯುಲಸ್. ಯಾವುದು ಜಾಸ್ತಿ ವೆಯ್ಟ್ ಹಾಕುವಾಗ ಕೂಡ ಲೆಂತ್ ಇನ್ಕ್ರೀಸ್ ಆಗೋದಿಲ್ಲ, ಅದಕ್ಕೆ ಹೈಯೆಸ್ಟ್ ಯಂಗ್ಸ್ ಮಾಡ್ಯುಲಸ್ ಉಂಟು ಅಂತ ಹೇಳ್ತೇವೆ. ಅದ ಕಾರಣ ದಿಸ್ ಇಸ್ ಅನ್ ಎಕ್ಸ್ಪೆರಿಮೆಂಟ್ ವೇರ್ ಯು ಕ್ಯಾನ್ ಅಂಡರ್ಸ್ಟ್ಯಾಂಡ್ several aspects of Young's modulus and elastic properties. I hope this will be very interesting topic for you. Say you can go through your reference books, the textbooks which is provided to you, where lot of examples are there, problems are solved. You simply solve the problems which are already worked out, which will be very useful for you, because once you have the calculator or the what I say log table, now you are not using logarithm table. So here why I am saying is you work out the same problem here. Say in this experiment, for example, say m is measured in gram, that has to be converted into, say suppose you are using, suppose you put 100 gram weight, okay, 100 gram weight, that will be 100 into 10 to the power of minus, say gram to kilogram ಮಾಡಿದ್ರೆ 1000 gram no minus 3 kg, that is the mass. Then radius is will be in millimeters, right? Radius is millimeter. Say 2 millimeter is the radius of the wire. Then 2 into 10 to the power of minus 3 meter. Correct? And delta L again, delta L will be very, very small. Correct? It may be a say 0.1 millimeter, 0.1 millimeter. That will be 0.1 into 10 to the power of minus 3 meter. Again, you see all these ratios, no, minus 3, minus 3, minus 3, putting them together is a challenge. Many times people forget to substitute these powers in the calculated results, and they will not write the powers. Remember, Young's modulus will be having some number followed by 10 to the power 9 or 10 to the power 10. Correct? 10 to the power 9 means most of the meters you can represent. Suppose it is steel, you can write even 1 into 10 to the power 10. That's also fine. That is Newton per meter square. Writing unit and calculating, substituting all the numbers very properly in the problem is very important. I hope you will be able to work out some of the problems in your leisure time, so that you get adequate training to solve the problems in this chapter. Otherwise, problems will remain very simple here. Only thing you should know how to manipulate, how to manage this powers, to the power. I hope any questions, if there are any questions, please ask. Otherwise, I'll stop my presentation. Thank you so much.
Thank you, sir.
Thank you.
ವಿದ್ಯಾರ್ಥಿಗಳೇ, ಈಗ ತಮಗೆ ಇವತ್ತಿನ ಉಪನ್ಯಾಸ ಕಾರ್ಯಕ್ರಮದಲ್ಲಿ ಯಾವ್ದಾದ್ರು ಡೌಟ್ಸ್ ಇದ್ದು ಮತ್ತೆ ಏನಾದ್ರು ಕ್ವಶನ್ಸ್ ಗಳಿದ್ರೆ ಕೇಳುವಂತ ಸಮಯ. Please ask any doubts and any questions about today's topic.
Any questions? Some, sir?
Chat box ಅಲ್ಲಿ ಯಾವುದೇ questions ಯಾವ್ದು ಇಲ್ಲ ಸರ್.
Okay, okay, ಸರಿ.
So ನಾನಲ್ಲೇ ಅವ್ರು ಏನಾದ್ರು ಕಳಿಸಿದ್ರೆ later on I send through your mail, sir.
Okay, sir, all right.
I send your mail ID and I send
questions are asked. No problem.
I send your mail ID and I send your phone number also, sir.
All right, sir. Thank you. No problem.
ಸೊ ಇವತ್ತಿನ ಉಪನ್ಯಾಸ ಕಾರ್ಯಕ್ರಮದಲ್ಲಿ ಎಲಾಸ್ಟಿಕ್ ಬಿಹೇವಿಯರ್ ಆಫ್ ಸಾಲಿಡ್ಸ್ ಎಂಬ ವಿಷಯದ ಮೇಲೆ ತಾವು ಕೊಟ್ಟಂತ ಉಪನ್ಯಾಸ ಕಾರ್ಯಕ್ರಮವು ವಿದ್ಯಾರ್ಥಿಗಳಿಗೆ ಹಲವಾರು ಮಾಹಿತಿಗಳನ್ನ ತಿಳಿಸ್ಕೊಟ್ಟಿದ್ದೀರಾ ಸರ್. ಸೊ ನನ್ನ ವೈಯಕ್ತಿಕವಾಗಿ ಹಾಗೂ ನಮ್ಮ KSA ವತಿಯಿಂದ ಧನ್ಯವಾದಗಳು ಸರ್. ಸೊ ಅದೇ ರೀತಿ ನಮ್ಮ ಅಕಾಡೆಮಿಯ ಅಧ್ಯಕ್ಷರಾದಂತ ಪ್ರೊಫೆಸರ್ ಅಯ್ಯಪ್ಪನ್ ಸರ್ಗೂ ಕೂಡ ಧನ್ಯವಾದಗಳು ಸರ್. ಹಾಗೂ ಈ ಒಂದು ಟ್ಯಾಲೆಂಟ್ ಸರ್ಚ್ ಪ್ರೋಗ್ರಾಂ ಕಾರ್ಯಕ್ರಮವನ್ನು ಆಯೋಜಿಸಿ ನಮಗೆ ದಿನನಿತ್ಯವೂ ಸಲಹೆ ಸೂಚನೆಗಳನ್ನು ನೀಡುತ್ತಾ ಬಂದಿರುವ ನಮ್ಮ ಅಕಾಡೆಮಿ ಮುಖ್ಯ ಕಾರ್ಯನಿರ್ವಹಣಾಧಿಕಾರಿಗಳಾದಂತಹ ಡಾಕ್ಟರ್ ರಮೇಶ್ ಸರ್ಗೂ ಕೂಡ ಧನ್ಯವಾದಗಳು ಸರ್. ಹಾಗೂ ನನ್ನ ಎಲ್ಲ ಆತ್ಮೀಯ ಮಿತ್ರರು ಹಾಗೂ ಹಾಜರಾಗಿರ್ತಕ್ಕಂಥ ಎಲ್ಲ ನನ್ನ ವಿದ್ಯಾರ್ಥಿ ವೃಂದದವರಿಗೂ ಹಾಗೂ ವೆಬೆಕ್ಸ್ ವೃಂದದವರಿಗೂ ಕೂಡ ಅಪಾರವಾದ ಧನ್ಯವಾದಗಳನ್ನು ಹೇಳುತ್ತಾ ಈ ಒಂದು ಕಾರ್ಯಕ್ರಮವನ್ನು ಮುಗಿಸುತ್ತಿದ್ದೇವೆ. ಥ್ಯಾಂಕ್ ಯು ಸರ್.
ಥ್ಯಾಂಕ್ ಯು.